Okay, we're going to take a look at the solutions of this autonomous differential equation and sketch solutions without actually solving it. Before starting, we note that the right-hand side here has no t's or x's, so which makes this an autonomous differential equation, which means that I can apply the techniques to find the equilibrium points and also assess the stability of these points. So first off, we have that y prime is equal to, if I factor this, I can first pull out the negative y squared. That gives y squared minus 3y plus 2. And then once again, I can factor the what's left and get negative y squared times y minus 1 times y minus 2. Okay, now there's a couple of ways to be able to assess the stability of the equilibrium points. The first way is by drawing a sign chart. We have negative y squared, y minus 1, y minus 2. So multiplied together, they give the derivative y prime. Equilibrium points are going to be 0, 1, and 2. 0 clearly, if y equals 0, clearly negative y squared is 0. Otherwise, it's negative, no matter if I plug in something to the left or to the right of 0. Y minus 1, that's equal to 0 if y equals 1. That is negative if y is below 1, and it is positive if y is above 1. Y minus 2, that's equal to 0 if y is equal to 2. It is negative if y is below 2, and it is positive if y is above 2. So multiplying, we get 3 negatives make a negative, 0. 3 negatives again make a negative, 0. 2 negatives times a positive makes positive, 0. Then 1 negative times 2 positive makes negative. So if the derivative is negative, that means the solutions are decreasing. Again, the derivative is negative, so the solutions are decreasing. Here, the derivative is positive, so the solutions are increasing. And finally, the solutions here are negative, so these solutions will be decreasing. So looking at the arrow pattern, here the arrows are getting closer to 2, so this one is a stable equilibrium. At 1, they're both going away from 1, so this one is an unstable equilibrium. And finally, at 0, one direction is getting closer to 0, but one direction is not, so this one is semi-stable. Okay, so that's one way of characterizing the equilibrium points is by looking at the sign chart and drawing these arrows. A second way of characterizing the equilibrium points is by looking at the derivative of the right-hand side. So here's my original function f of y. Let me recopy that. Negative y to the fourth plus 3y cubed minus 2y squared. If I take the derivative, I get negative 4y to the third plus 9y squared minus 4y. Okay, now let's plug in and see what happens. F prime of 0. F prime of 0, let's see if I plug in 0, I get 0, 0, 0, so that's equal to 0. More on that later. If I plug in 1, I get negative 4 plus 9 minus 4, and that's equal to 1, which is not important. The important thing is that that is greater than 0. And so because this is greater than 0, this is an unstable equilibrium, just like we saw here. Next, if I plug in 2, f prime of 2 is equal to, let's see, plug in 2, I get negative 32. Plug in 2 into this, I get 9 times 4 is 36. Plug in 2 into here, I get 8, so I get negative 4. The value is not important. What's important is that it's negative. So because f prime of 2 is less than 0, this works out to be stable, which we saw here as well. Okay, now the last thing we haven't figured out yet is what about 0 here? So this was 0. In order to be able to assess the stability, we have to figure out the second derivative. So if I take the second derivative, I get negative 12y squared plus 18y minus 4. And so the second derivative is equal to negative 4. That is not important. The important thing is that it's not 0. So f prime of 0 is 0, f double prime 0 is not 0, and so this proves to be semi-stable. If this was equal to 0, then the test would fail, and I would have to resort to the sign chart to figure out the whether or not 0 is stable or not. Okay, so we're almost ready to start sketching solutions. We have one thing left to do to help give us a good picture, and that is to look at the points of inflection. To find the points of inflection for the solutions, we're actually going to take a look at the first derivative of the right-hand side, and set that equal to 0. All right, now clearly I can factor negative y out. That gives me 4y squared minus 9y plus 4 equals 0. So y equals 0 is the solution. Also, I can use the quadratic formula to solve for what the values of y that make this part equal to 0. So y is equal to 9 plus or minus square root of 81 minus 4 times 4 times 4 makes 64, all divided by 2 times 4 for 8. So 9 plus or minus the square root of 17 over 8. Those will be the points of inflection. And I worked this out on my calculator ahead of time. That's 1.6406 and 0.6096 approximately. Okay, so with all that, let's start sketching the solutions. Okay, so here's 1. There's 2. So that's an equilibrium point. That's an equilibrium point. 0 is also an equilibrium point. And we've established that I have points of inflection at about 0.609. So I'm going to put that in a very, very light red here. So that's about maybe here. So this very thin red line, that's a point of inflection. Also 1.64, that's roughly here. That will also be a point where a point of inflection where the solutions change concavity. Okay, so let's start. To the left of 0, the solutions are decreasing. Okay, so that's easy. There are no points of inflection, so to the left of 0, the solutions are decreasing. So I've got all these curves that look like this going away from 0. Between 0 and 1, the solutions are decreasing, going away from 1, getting closer to 0. So I have to have things that go away from 1, get closer to 0, and they change concavity at this pretend red line that I just drew. So the solution goes like this, and then changes concavity to get closer and closer to 0. So it comes like this, changes concavity to get closer and closer to 0. Okay, like this, change concavity. Over here, there's no change in concavity, but if I were to extend this further, it would change concavity here and then be concave down as I got to going to 1 in the other direction. Okay, between 1 and 2, it's increasing from 1 toward 2. So increasing to 1 toward 2, and it changes concavity at this line. So increases toward 2, changes concavity here, and then it's concave down as it gets closer to 2. Increases, gets to this point, changes the concavity as it gets closer to 2. And so we get these pretty good curves like this. And then finally, to the right of 2, the graphs are decreasing because 2 is stable. And so there's no change in concavity, and so these just simply get closer and closer to 2 as t gets large. So we see that 2 is stable, 1 is unstable. They get further away from 1 but get closer to 2. And 0 is semi-stable. It's closer to 0 from this side but gets further away from 0 as below 0. So that is a sketch of the solutions without actually solving the differential equation.